Thanks. So now we have the last talk before a coffee break, and I have the pleasure of asking Graeme, who seems to have the next generation detectors as he's back to, behind his back. Yeah.
Even better if you can hear me. So hopefully you can.
Yeah, now we got it.
I got it 2 hours ago, so it appears to be working. That's good. Right. So yes, we do not have an Eiger at work that is as big as this curtain. If we did, we'd have very, very big data handling problems. Yes, I'm just going to talk a bit about Eiger data handling at Diamond. We've already heard a little bit about these detectors, so I mean, I'm not assuming you'll know what's going on, but the idea is that we are trying to capture data from these real time and analyze it at the same time. Now, getting this done is not just like a one-person job. There are a lot of people who have contributed to this work. So, you know, we couldn't have done it without all of these people. It's important to note that it's not just a software problem. You have to have the networks, you have to have the infrastructure, you have to have the file systems. So all of these components are what makes the system that I'm presenting here work. Okay, so the context is basically this, that we start off with user crystals. They come along, they're on little pins, they live loads of them in a puck. They get loaded up, and what we really want to do is automatically center them. So the way that we center them is you load the crystal up, you use a detector that looks a bit like this, you capture diffraction images that look a bit like this, and really what you want to do at the end of the day is get to a picture that looks like this. This is the science data, this is what people are interested in, right? But we can't get to that before we've actually found the best point on the crystal to shoot. And the way we do this is essentially we raster over the crystal, taking data as we go, and then basically find the best spot on the crystal by looking for the spots, and then say, here is the best spot. And we do that in a two-dimensional array, and then we rotate and do a one-dimensional scan that way. So normally we wouldn't necessarily have such tiny grids, but these grids can be up to thousands of images in size. So what you want to get to at the end, essentially, is have the X-ray beam lined up on a good bit of the crystal to collect the data set from. So making this work it really depends on the structure of the data. So the previous generation of detectors we had wrote CBF images that Herb Bernstein mentioned yesterday. And this worked very well because you capture an image, the image ends up on disk, you can analyze the image and you can push the results back to a database. So this scales very nicely and makes the job of a sort of data analysis scientist very easy. But the problem is that GPFS hates having thousands of small files. And by small, we mean like, it's a few megabytes. And so what would happen is you'd end up collecting data from 10 crystals or whatever, 10,000 frames off each, have 100,000 files in a directory, and GPFS would take 1.5 minutes to list them. So this isn't very good. And also this system simply cannot cope with detectors that are running at 500 frames a second. So when, sorry, I am having slight issues here controlling the slides for some reason. Right. So the Eigers, so these are actually basically a turnkey system that we get from Detectors, and you can either use the 0MQ interface that sends you out basically compressed frames over a network socket, or you can get the the detector computer to basically save files as HDF5 and then read them out over HTTP. So we use the 0MQ interface, which allows us to basically take the data, capture it with something that's called Odin, that's developed by the controls group at Diamond. This is then basically used to make sure the data end up on GPFS. The way we had it initially set up was that we'd write the data to an HDF5 file. At the end of acquisition, we would submit a job to the cluster that does the analysis. That would then churn away through the HDF5 file using HDF 1.8, and then it would give you some results. So this meant that we could very easily acquire data at 500 plus hertz with a 16 megapixel detector. That was absolutely fine. The acquisition worked perfectly. The problem was you couldn't analyze the data while it was being acquired. So you had to process the data at the end of the scan. And that essentially meant that it was very slow. So the user feedback was what we could call not favorable, in the sense that if you do a big grid, you can capture the grid in seconds and then wait for 1.5 minutes for it to be analyzed. And the feedback was basically, this new fast detector is a lot slower in actual use than the old detector. And so we had to fix this problem. And so the first solution we came up with, because we were still stuck with HDF 1.8 for all the reasons that previous speakers have talked about, was we came up with a nasty hack, which was that we took the 0MQ packets that were sent to Odin and got Odin to forward them to something we called a stream dumper. And this is basically just a little nasty piece of Python that takes a 0MQ packet out of a network socket, takes the packet and shoves it on disk. And basically we extended the analysis software called Dials to read this dumped file format, and then actually everything just worked. Now, of course, anybody who works at a facility will be familiar with the idea of a temporary workaround, where you have a workaround. Yeah, we'll do this for a few months, and then we'll replace it with something proper. So 2 years later, we were still using the temporary workaround. Now, it had some really good benefits. It would work pretty well for about 1,500 to 2,000 images, which is bigger than the majority of grid scans. We could use, because we were basically dumping each packet as one file, we could use the existing infrastructure for doing the parallel analysis, because it's essentially the same shape problem as analyzing the CBF files. And we can analyze the data as it's being acquired. There are some nasty properties of this nasty hack, which is that it's extra load on the file system. And of course, you have also gone back to the problem of capturing many thousands of small files. So that's not so good. But we kind of worked around that by putting them into temporary directories. And the main reason that we actually got stuck with this is that you're limited to about 2,000 frames before the entire system backed up. And that meant that we could not use it for doing serial femto or SSX, serial crystallography on a synchrotron. So that is something that we really wanted to be doing. So we had to come up with a better solution. But the key point was, nasty hack worked literally for years. So in the meanwhile, right, while this 2 years actually came and went, HDF5 110 became commonplace. It was out there in the wild. And key point is some very, very useful features were added in the more recent HDF5 1.10 libraries, including the ability to check the chunk size. So we are using direct chunk write in Odin. So we take the compressed packet and we use direct chunk write to put that in the HDF5 file. So if we can check the chunk size, we can see whether or not that chunk has been written. So if we're using SWMR format, we can actually say, has the data for this frame been written? If it hasn't, I shall wait and come back later. If it has, I shall analyze it and move on, which means that we start to move into a system that's able to work a bit more like we had with the CBF files, but without the CBF files. So specifically, it was adding the get chunk info by chord function into HDF5, the H5Pi library in 3.0 plus small numbers, that meant that we can actually now do this work. And that put us in a position where we can revisit the idea of using the HDF5 files for live analysis. So that puts us basically into a point where we are actually now really using all of the HDF5 1.10 features that have been around for a couple of years now. So SWMR, virtual datasets. So the way this is working is obviously everybody in the room knows what these things are. SWMR, we've got single write, multiple read, and this is basically using the HDF5 file as a directory, and you can add and remove chunks, everything's fine. The virtual dataset is there so that we have the place where the data are going to end up being a virtual dataset. And then inside that, it points to HDF5 files that will be written in the future by Odin. Now, obviously, if you go to read those files, you'll find that they're empty and you just get fill values until the file is written. But what we actually do as part of the analysis is actually dismantle the virtual dataset so that we can actually watch for when the files appear, and when the files appear on disk, we can start analyzing them. But also, if you come back to it later, you can ignore the fact that we're using SWMR and virtual dataset and just read entry data and get on with the analysis. So we have something that's called a master file. This is essentially the top level file. It defines the full extent of the data. It says this is all the metadata you need in the experiment and so on and so forth. That is written by the data acquisition system, which at Diamond is called GDA. So what we then have is a separate system called Odin that is basically capturing the data from the 0MQ stream and writing that to disk. And because we know the overall shape of the system, we can guarantee that this should work. And so what we did is it extended the system that was previously watching for the appearance of CBF files to actually watch for chunks appearing inside these HDF5 files. And to be honest, it actually works quite well. So what we now have is essentially topologically the same shape as we had before, but working. So we can analyze the data in real time. We can scale up with as many CPUs as is necessary to do the job. Our GPFS system is really happy because it's handling, a handful of big files. So each of our files contains 1,000 frames, and there's no real limits to how long you can run this. The big problem with this is there's no real limits for how long you can run with this. So to give a real life example, so this is doing some scans on one of our beamlines IO4 with one of the new generation Eiger 2XE 16M detectors. So this is 6,000 and some point grid. It's doing 2 millisecond exposure at every point and then moving on to the next point. We trigger the detector at every point in the scan. And so what you can see here is the top blue bar is the overall time that the data acquisition took. So this is from the user pressing go to the scan being complete. And you see that there's a good few seconds at the beginning of kind of miscellaneous non-activity before the scan actually begins. And then fairly shortly afterwards, you'll see the file watcher start to notice that frames appear. Then time passes, and then a few seconds after the scan finishes, the file watcher stops noticing that files have appeared. And then there's a bunch of time spent analyzing those frames because we were not set up to deal with the fact that people are going to throw 6,000 frame data sets at this system. So in real terms, the scan took 20 seconds. It was actually running on average at about 280 frames a second because of the time it takes to move from one position to the next. And in real terms, the overall latency between a frame being captured and a frame being readable was systematically about 3 seconds, which is as good as real time, as good as we can get in terms of near real time. And at this point, we became acutely aware that we're going to need more computers to do this work, but that's outside of context for this presentation. So, 800 cores we were using, or that's not a whole cluster, but it's quite a bit. And actually, could we analyze that data from these files in that time frame? And actually, we re-triggered the analysis, and it turns out that yes, you can analyze all the data nearly in real time. So, if we put enough compute behind the system, we could be doing this in pretty much real time. And there are conversations ongoing about looking at different ways of writing the analysis to use more modern sort of CPU architectures. Okay, so there are some problems, and this is the kind of problems that manifest themselves in real life, that all of a sudden now you've removed the limits on how big the scans can be, and you suddenly realize that you just created a whole load of more problems. So for example, this is how the scan looks in our online viewer, and you'll see that you can't really read the image numbers because they're all over each other. So yes, there are some problems there. What I would say though is, back when these detectors came out, there were a load of different opinions of how you can store the data. And as Herbert pointed out yesterday, remarkably, actually, the community managed to kind of rally around and come up with a sensible answer. But it's important to notice that this sensible answer is actually sensible. So if we look at this data, 6,000 frames, about 16 million pixels each. If we'd taken the old CBF format, that would be about 100 gigabytes of data. In HDF5 format, this is about 10 gigabytes with a bit shuffle and LZ4. We've got about 3 orders of magnitude fewer files. So this keeps our file systems very happy. We can keep up with the data analysis, we can keep up with the acquisition as fast as the detectors will go. So this is, this is a real benefit to the end user, who is ultimately the people who we want to keep happy. We've removed all the limiting factors. And what I would say as well is all of this stuff that has been described here is actually open source. So, if you are a facility somewhere else, there's literally nothing stopping you from trying to get this up and running yourself. Obviously, there's work we need to do, like make the live analysis more efficient and so forth. But overall, I think the system has been very successful. Again, if you remove limitations, what you will find is that you suddenly discover all the other problems that you weren't aware of. I will say that actually in our systems, SWMR virtual dataset do appear to be actually pretty reliable in production. So there was a lot of nervousness around when we moved this way, but actually we have not had problems with virtual dataset and SWMR. We've had other problems, but not with those things. So the format itself is very robust. We can only do this not because we just bought a really expensive detector, but because we've got a very good detector and a whole load of other stuff that makes this possible. And really, there's nothing stopping us from doing the analysis real time. And I can see lots of the faces have appeared, which is good because I'm done. Thank you.
Thank you. Thank you, Graeme. Very, very interesting. I don't see, there was a question about if you're using direct chunk right, but I think Ulrich has already answered.
Yep.
I don't know if the other questions, Thomas, did you have a question? Did someone put their hand up?
Yeah, no,
I had a, okay.
There is a hand up.
I can't see it. Well, please go for it.
I put the hand up. It's like, okay, what spot finder are you using? Because what I understood, you have a spot finder.
We're using the dials. We're using the dials spot finding, but inside some custom code that watches the files a bit.
So this is where the HDF5 file is still needed, like, I guess.
Yes, I mean, the point is that actually using the HDF5 file means that the data is there forever.
Mm-hmm.
Yeah, so we are using the dial spot finding, but if we're using this in a serial crystallography case, which is something we want to do real soon now, then we can do the initial hit finding and then subsequently more thorough analysis later on. And you never have any worry about the data being interrupted. It's always, the first job of the acquisition system is to get the data to disk. And then everything else is, nice to have afterwards.
Yeah, some questions. Some great. Thanks.
I had one very stupid question, which was you're running at 280 hertz, so you're producing about 1,000, and you say there are 1,000 frames on average in a file.
Yes.
So it means you're producing a file a second, yeah?
Well, no, I mean, so the detector runs at up to 560 hertz, so it's a file every 2 seconds.
Okay, but I'm wondering, is that in any way linked why you wait 3 seconds on average, because you wait for the file to be finished written, right?
No, because you can read the data as it's being written.
Okay.
So one of the tests we did, because I mean that is a very reasonable question, by the way, was actually running acquisitions at 10 hertz. And if you run acquisitions at 10 hertz, you can still read the seconds, read the frames up to 3 seconds, about 3 seconds later. But that 3 seconds allows for the fact that the detector gets triggered. The image has to get from the detector head to the detector computer, formed into an image, compressed, sent down a network, captured by the acquisition system, written to the HDF5 file, flushed, and then noticed by a computer in a cluster that's 400 meters away. And that whole process is what gives you the 3 second delay.
Okay, so you tested it with different rates. Yeah?
Yes.
I would have one interesting comment. Like I was also interested with your limit of 2,000 frames. Yeah, from what I saw, for example, at Maxwell laboratory, they before they were doing rotation experiments with 1,800 frames. Not sure why. From some experimental reasons, likely, but when everything started working like better, also thanks to the HDF5 files. And like a good support for Eiger, like they are now using expositions with 3,600 frames, like 2 times more.
Sorry, I've just got to clarify something there. That 1,800 frames was for doing the raster scan, and that was because we were using the nasty hack that it copied the data to another file. I mean, people routinely do rotation scans with 30,000 frames. Okay, so there is literally like you can run these detectors flat out, and the limiting factor is actually how quickly the detector computer can read and compress and send the files down the wire. So actually the limiting factor, I believe, in the amount of time that you can run the detector at full frame rate is the limiting factor is how much memory is in the detector computer. Yeah. Because it's got to compress the images. If you slow it down slightly, so if you run at 400 frames a second, we can run basically forever.
Sure.
And you know, running a big detector at 400 frames a second for a long period of time generates a heck of a lot of data.
Yeah, causes other problems.
It does indeed. Yeah.
Thank you very much, Graeme, and thanks to all the speakers.